All right, welcome to Module 15, Lesson 1, which is Forces Within the Earth. So a fracture is when a rock breaks. So you can see this rock here is broken, and a fracture. And when we learn about fracture and cleavage, remember fracture is when it breaks unevenly. So this would definitely be fracture. It's not breaking evenly at all. Cleavage would be where it breaks with an even pattern. All right. So if we talk about earthquakes, we talk about strain and stress on rocks. Those are two different terms. So stress is the force that's acting on the rock. So there's different types of stress. There's compression, tension, and shear, which we'll talk about. So here's our different types. So no strain would be the rock is normal. So you can see the squares there are completely normal. And then if we go through compression, compression is squeezing together. So think of something as squeezing. And so it's going to cause it to look like this. And then tension is pulling it apart. So think about when you have a rope and you want to make tension on the rope, so you pull it apart. So that's what's happening here. And so that's tension. So if we think about the plate boundaries, compression would be where you've got two plates colliding, right? They're coming together and they're squeezing together. And then tension is when they're pulling apart. And then shear would be like our transform boundary, where they're kind of sliding past in opposite directions. And so those are our three types of stress or strain, I'm sorry. All right, and so let me go back to that actually. So this would be our types of stress, and then the strain is what's happening. So the strain is like what's happening to those little squares. So you can see that they're all shaped differently. So that would be the deformation that we would see happening on those rocks. All right, so rocks can be twisted and squeezed and stressed, and eventually they're going to break. And when they do that, they create an earthquake. And so they also deform. So they become elastically deformed, which means that think of a rubber band. You pull a rubber band and it gets super tight. So that would be tension. And then eventually it's going to break. And so when it breaks, it goes back to its original form. It's broken, but each piece is no longer stretched. So rocks, in a sense, do that. So rocks have this thing called elastic rebound. And so when they're stressed and strained, they deform. And so when that stress is relieved, like in an earthquake, then they, in a sense, snap back and relieve that stress. All right, so we can see this on this diagram, this graph, and then also think about a stick. So if you take a stick and you're just kind of slowly bending it, it's going to bend and curve, but then it's eventually going to fail. So it's going to break. So here's where we have that elastic deformation. So we've got the strain of the stick being bent. And then this plastic deformation is where maybe when we let go of the stress, the stick is like a little bit bent. And then eventually it breaks. So it's just going to crack in half. And that would be failure. So rocks do the same thing. And different rocks do different things. So some rocks will have more stress. They can handle more stress. And some rocks can't. And so that just depends on the rock type. All right. So like I said, it depends on the material. So different rocks stress and strain differently. Some rocks might break really fast. Some rocks might not. Temperature also plays a big part. So if there's temperature, like if there's heat involved, then the rock will bend and be able to withstand the stress a little bit better than if it was cold. So think about in the middle of winter, like now, outside, you go to sit on like patio furniture that's plastic and it literally just cracks. But in the summertime, it didn't do that. And so temperature causes things to react differently, especially if they're older or they've been through stress more often. So rocks will do the same thing. All right. And then a fault is where that structure broke. So a fault is where the rock deforms so much that it can't stand it anymore. So it actually breaks. And that's also where we see earthquakes. So earthquakes occur along these faults. And here we can see different types of faults. So we've got reverse and normal faults. So what we look for when we're talking about these types of faults is hanging walls and foot walls. So a foot wall sticks out like a foot. A hanging wall you can hang off of if you were to separate the other piece. So if we're looking at these two here, this piece right here sticks out like a foot. So you can picture like a leg up here or something. And then if I were to remove this piece, I could hang off of all of this section And so that's the hanging wall. And so if we look at this picture here, I can see the foot wall is this one. So this sticks out like a foot. And if I had a leg up here, that's what your foot would do, is stick out. And then if I were to remove this piece right here, I could hang off of any part of this other block. And so that would be our hanging wall. And so a reverse fault is when you've got compression. So you've got two plates coming together, and the hanging wall is going to go up relative to the foot wall. All right. And so here we can see a foot wall. And here we can really see it because you can see this sill in here. So this is a sill, this different colored rock. So here we've got the foot wall. And here we've got the hanging wall, and here's a person standing there. So this is a fairly large sill and a pretty obvious fault here. So hanging wall is here, foot wall is here. And so you can see this is different, right? So the hanging wall went down relative to the foot wall. So this would be a reverse fault. So a reverse fault is when you've got tension stress, so the plate is pulling apart. And then strike slip is basically slipping back and forth. So you really don't have a hanging wall or foot wall. It's just sliding back and forth. So the San Andreas Fault is a really good example of this. And you can see this right here. And this is kind of crazy. This is cool. But this field was planted, then an earthquake occurred, and it's on a transform fault. So this portion, this piece moved this direction, and this piece over here moved up and to the right. So you can obviously see that there. And then this is the San Andreas Fault. So the San Andreas Fault is also a strike slip fault. All right, so here's our three types. We've got reverse, normal, and strike slip. So reverse is compression. It squeezes together. Hanging wall goes up, foot wall goes down. Normal is tension, and it's the opposite. So hanging wall goes down, foot wall goes up. And then strike slip, it's just simply sliding back and forth. And we'll do a lab that you guys will mimic these things with Play-Doh and show me the different types of faults. All right, so earthquake waves are caused by faults. So when the rocks move, they create earthquakes. And so that's basically seismic waves. So these seismic waves come out and we can measure them. And so there's a couple different types of seismic waves. There's primary waves and secondary waves, and then surface waves. So primary and secondary are in the earth. Surface waves are, like it says, on the surface. So here's a P wave. So P wave stands for primary wave. And so you can see it's squeezing the rock and it's moving in one direction. So this is called a primary wave. It's fastest. So it's the fastest traveling wave because it's traveling in a straight path. So you can see it moving along there. And then secondary waves are called S waves. And so S just stands for secondary. And they move slower. So they get there second. And they move slower, obviously. So here is that S pattern. So they're moving perpendicular to the direction of the wave. So you can see the particles are moving up and down perpendicular to the wave direction. So S waves are taking longer to get there. So that's why they're secondary waves. And then third wave is called a surface wave. And surface waves are just basically on the surface. So when a P and an S wave reach the surface, they become surface waves. And surface waves are what we feel. So we don't feel P and S waves. We only feel these surface waves because we're on the surface of the earth. All right, so when an earthquake occurs, it starts at where the rock actually broke. And so that is not always right on the surface. So here in this case, we have the focus. And so the focus is where the earthquake actually started. So that's where the slippage or the break actually occurred. And the break occur all along this fault. So you can see it could occur all along here, but it's going to start somewhere. And so it starts on the focus, and then that energy, those waves radiate in all directions. And so they radiate in all directions, and directly above the focus is what's called the epicenter. And so you guys have probably heard that with earthquakes, whenever we have one, they always refer to where's the epicenter. So that's directly above the focus, and it's generally where we're going to have the strongest waves. So if you're in an earthquake or you're in a city, it's going to be where the most damage occurs. Is the epicenter. So it's directly above the focus, and the focus is where the earthquake starts. All right, so we can see the epicenter here. And so what we're going to look at is some earthquake data, and it shows different types of waves. So this is kind of cool if we look at this. So here is a map of North America. And so this is the Pacific plate. Here's the North American plate. And this little plate right here is the Juan de Fuca plate. So I'm going to zoom in a little bit. And you can see right here, here's the Juan de Fuca plate. So this plate is sliding underneath the North American plate. And the Pacific plate is kind of going this direction. And the Juan de Fuca plate is going this direction. So here's our subduction. So notice how this is where Lassen and Shasta is. And so we get volcanoes occurring up here, right along that Juan de Fuca plate. And we don't get them any farther south, and that's because we don't have subduction. We have a transform boundary. And then what's kind of cool is to click on these earthquakes to see what's going on. So this one was in Viola. So that's towards Lassen on 44. And so, 44. And so it was a 2.8. You wouldn't be able to feel that. So it needs to be at least a 3 before you can even remotely feel it. You'd be like, have to sit still and maybe feel it. So it was 1.6 kilometers deep. That's fairly deep. And then if we look at this one was in Dunsmuir. This one is 1.1 kilometers deep. It was a 2.5, so definitely not felt. So we can see that there's quite a bit of earthquakes. So just looking at this, we can see there's earthquakes all over. And if I zoom out a little bit, notice where we see most of the earthquakes. Think about it. So look at the picture. Where do we see most of the earthquakes? So you're going to see them along the plate boundaries. So here's our plate boundaries. Here we've got the Pacific plate. This is the Ring of Fire. We've got the Nazca plate. We've got the North American plate. We've got the African plate. We've got, let's see, what else do we have? Antarctic plate. We've got the Eurasian plate, the African plate, and then we're back over here to South America. So it kind of repeats itself. But it's kind of cool because you can see most of the earthquakes occur along the plate boundaries. And that's how we know where the plate boundaries are, is because of earthquakes. So without earthquakes, we wouldn't know necessarily. They're not just obvious, the earthquake or the plate boundaries. And so the earthquakes help us to define those plate boundaries. All right. And I think that was it. Let's see here. Yep, that was it. So I will see you next time.